We go beyond the journal articles and into the laboratory and the field as scientists share their discoveries in a way everyone can understand. It's science explained. You're listening to Science Sound Off on Texas A&M Health Talk. Welcome to Science Sound Off. I'm Christina Sumners.
And I'm her co-host, Tim Schnettler.
And we're here today with Dr. Zhilei Chen. She is an associate professor from the Department of Microbial Pathogenesis and Immunology at the Texas A&M College of Medicine. Welcome to the show.
Thank you.
We're thrilled to have you here today. So your research is on protein engineering. Is that a fair statement?
That's right. Yeah.
Okay. So what is protein engineering?
Okay, so protein engineering, basically, we try to engineer proteins for different applications. So it can be used in laundry detergent. It can be used in medicine. So that's what we are interested in. And it can be used in materials to build, coatings for implants. And also can be used for making materials to grow cells in it. So kind of a big field, but we are most interested in engineering proteins for therapeutic application.
So these are drugs that are different from the normal pharmaceuticals that we take. How are they different from just the drugs you usually get in the pharmacy?
Yeah, so I would say in the 19th century until now, all the medicines are made of small chemicals. So they are made by chemists and they are engineered by the medicinal chemists who make these molecules. You can think of different small atoms, putting them together to make different drugs. So with the development of the recombinant technology, in the recombinant DNA technology in the 20th century, so it kind of opens the door to a new set of tools people can use to generate proteins. So so that's kind of what we are doing. We try to make medicines out of proteins because in the nature, so proteins are our natural defense mechanism. So our body uses protein to fight off infections, various kind of diseases. So so we kind of try to borrow this page from nature and try to use that to develop medicines to treat different diseases. So I guess, the protein medicine everybody knows about is the antibodies, right? So antibodies are proteins, and they are basically engineered by the body to fight various infections. So throughout your lifetime, you get different infections. You are affected by different, having different insults over different time. And your body is constantly engineering different antibodies to fight off this infection over time. So what we're trying to do is try to do this, help in case someone who is not able to fight off the infection themselves, then we try to give them a boost, kind of like when you get sick, you take a medicine. Some people will get over the sickness just by themselves, but sometimes you need a little help with these medicines. So we try to engineer proteins that can help people get better quicker.
That makes sense. Okay. And so it really is taking the body's own natural ability and just kind of boosting it, like you said. But with recombinant DNA, you can kind of build these building blocks to do almost anything. Is that right?
I wouldn't say about anything, but a lot of things. Because proteins are very diverse, and the protein can have a lot of functions. So usually, I would say most proteins, they cannot handle high temperature, very harsh conditions. But some proteins do, just like most organisms cannot live at very high temperatures, but some organisms do, and they evolve ways to do that. And usually by having their proteins with different properties, like thermostable or stable against these different chemicals. So so you can engineer protein to have many different properties, almost unlimited variety of properties the proteins can have.
You mentioned fighting off the infection and some people not being able to fight off the infection. Is that something maybe that this is being developed for towards someone who's already sick with something like cancer or something like that to help them fight off other things that happen when they're dealing with this?
Yes and no. Say kind of just like a medicine, right? So a drug can, for example, somebody gets a cold, most people get over a flu pretty quickly. Some people don't. So we literally just try to use protein to mimic these small molecules to have these different properties. So I want to say, the biggest advantage of protein versus a small molecule is when you take a drug, the common thing the doctor say would be a side effect. What would be the side effect?
Right.
So the side effect usually comes, I would say almost all the time, it comes from the small molecule. Because it's so small, it targets your target, but it also targets something it's not intended to, because it does not have this specificity that can be so specific to your target protein or a receptor in your body. But protein is much bigger, so the biggest advantage is can generate to bind to your target with much higher specificity and affinity. So as a consequence of that, it will have much fewer side effects. So side effects is much reduced compared to conventional small molecule drug.
Because it's just not affecting all the things you don't want it to be touching.
Exactly,
Okay.
yeah. So that's kind of with the body, we all have so many different antibodies.
Right.
We don't have side effects.
Sure. Usually, yeah. So you recently had an article in the journal PLoS Biology, and you were looking at C. diff, the bacteria we know, C. difficile. Tell us a little bit about that research and what you all found.
Oh, okay. So this is actually a project initially started with the College of Medicine seed grant. So the C-Star Foundation gave us the seed grant, kind of allow us to generate the initial results for this study. So C. diff is an infection that affects, I would say, millions of people each year. It's actually the number one hospital-acquired bacterial infection, and which leading to death in patients. So C. diff is a bacteria that's kind of everywhere, in the environment, but it's specifically affect hospital patient in the hospital because when patient take antibiotics, it kind of believed to be the major reason where people will acquire the C. diff infection. The problem with C. diff infection is it kind of recurs. So people can have 2, 3, 4, 5 times infection.
Okay.
And it kills, I would say something like maybe 30% of people would die in the 30 days after the initial infection. So it's actually kind of a really big problem. So CDC consider that to be the top one, urgent problem we need to deal with in this country. So C. diff is a bacteria that's once it gets into, it's a spore that's kind of floating around in the environment. Everybody can breathe in, eat, it gets into your stomach. And unfortunately, usually the stomach acid would kill most of the bacteria. In this case, the stomach acid actually activates the spore, so allow the bacteria to germinate, and then it germinates in your stomach, and it goes into your gut, and it basically kind of just proliferate in your gut. And once these bacteria grow, they secrete toxins. People don't really know why the bacteria secretes toxins because they don't need to secrete toxins.
You think they wouldn't want to kill the host.
Exactly. They don't need to, but they do. And then once they secrete the toxin, these toxins enters the epithelium cell, the cell that line in your gut, and kills these cells. So as a result of that, you develop these colitis, which is kind of like a canker sore in your mouth, but it's in your gut, and it can be really painful and causes bloody diarrhea. So telltale sign for C. diff infection is a bloody diarrhea. And people can have, recurrent infection, and so normally the way we treat the C. diff infection is by using more antibiotics, try to kill all the bacteria. So it usually works, I would say, pretty well, but kind of in the recent years, due to the development of antibiotic-resistant bacteria, so the cure rate has been going down. And then you have to do it again, give them more antibiotics if they get an infection again, the next infection. So that's kind of the problem. So what we want to do is try to develop a protein, specifically something that can be somebody can just drink it, and it will enter the gut and neutralize these toxins.
Very cool.
So we don't have to affect the bacteria growth directly, but we can prevent the damage that are caused by these bacteria. So this protein we engineered, I guess the scaffold we chose is called a DARBin. It's a design anchoring repeat protein. So it's a scaffold. We chose this scaffold because it was found to be really stable. It's a protein that can endure very high temperature and then, kind of fold very stably. So with that, we engineered this protein to bind to the toxin. So specifically, one of these toxins is called the TCDB. So we, I guess the postdocs in my lab, they worked really hard on the project. So they first found we generate a library. So the technique we use is called directed evolution. So it's actually got Nobel Prize last year. Frances Arnold is my academic grandmother. so she is the founder of this directed evolution principle, and that's what we use for protein engineering.
Okay.
So the concept is rather simple. So just like a natural evolution, where it's a process where mutations happens randomly, and that is coupled with a selection pressure that allows the nature to select for organisms with more fitted properties. So it's kind of responsible. For example, that we have many different dog varieties, right? So
Sure,
they all come from wolf, but because of these random mutation coupled with selection, you are able to get dogs with. They almost look like two different species when you compare a Chihuahua with a Great Dane, right? So in protein engineering, we do something very similar, but we do that in a test tube.
Okay.
So we have a gene, which is a DARBin. So it does not bind to our target toxin, does not neutralize it, but we introduce mutations into this gene. So in this case, we create a library of these DARBins, about 10 to the 9th. So that's a trillion. Is that a trillion? So we have 10 to 9 different DARBins, and we subject them. We express these DARBins on phage, which is a bacteria virus. So, and then we select for these phage that can bind to our target toxin. So from there, we further screen the library we have for those ones that can, just because they bind to toxin does not mean they can neutralize the toxin. So from all those binders, we did a secondary functional screening. We look for those ones that can neutralize the toxin. And that's how we derive a first panel of 12 different DARBins that have a very strong neutralization activity. So from there, we did a secondary screening. So we try to combine these 12 DARBins in a random fashion, see if they can have something that work even better. So that allows us to get a second generation DARBin, which is a dimer that it turned out to neutralize the toxin at picomolar EC50. So that's a really, really strong potency for these DARBins. So, and then with a collaborator in Professor Junjie Zhang, so he helped us to solve the cryo-EM structure of the toxin in complex with our DARBins to help us understand how do these DARBin work, the mechanism of action. So and he generated some really beautiful EM structure images for us. And another co-author on the paper is Professor Han Pingfen. He is from University of Maryland. And then he helped us did the in vivo study to see whether these DARBins can protect from these toxin challenge.
So you've basically created these proteins and shown that they seem to work in animal models. What's next? Are you going to move them forward, or?
Yeah, so that's our goal. So I guess what we are doing right now, so we have submitted a patent application through the A&M. And in the second generation, we want to basically increase their stability further, because in the gut, we have all these digestive enzymes. So for something to work really well in the gut, they also need to be stable against these proteases. So so we have some data that haven't been published. We were able to create do a I would say maybe third generation engineering to get them to be very protease stable. So in the next experiment, we want to test it in additional animal models. So basically it's in a model where we can challenge the animal with the spores of these bacteria and see if our DARBins can protect them from these the toxicity of these toxins.
I want to back up a little bit. You mentioned that this is a common thing in hospitals, and that the CDC is that's identified as one of their top priorities. Why is it such a common thing in hospitals? Why do you see this infection in hospitals?
Oh, it's just because in hospitals, people are taking antibiotics, right? Especially in hospitalized patient. So the doctor usually give them a lot of antibiotics when they are hospitalized. And because of these antibiotics, that allows these bacteria to kind of an opportunistic infection, allow them to take residence in these patients. And then, even once they get discharged, when they go home, they realize, I'm having bloody diarrhea, and I have to come back to the hospital. So it's a major reason for people to come back and be hospitalized again and then again because of the recurrent infection.
It's ironic that a bacteria infection can be caused by antibiotics. I don't think most people really realize that happens.
Well, I mean, considering, antibiotic resistance is a global problem, right? So the more antibiotic we use, the more we have to use it to kill the bacteria. So we don't have a good solution to it. So I think that's why the NIH is looking for a way to treat this bacterial infection without without fostering more antibiotic resistance development.
So even when we create new antibiotics, then those bacteria become resistant to those, and it's kind of a continuous cycle. But your approach would bypass that altogether.
Hopefully, I mean, that's our goal. So hopefully, I guess one of the way to treat infection is try to leave the organism alone and then deal with the effect of this infection, right? So in this case, C. diff alone, it's actually they are not pathogenic. In fact, people have done a trial where they just feed the people with these strains of C. diff that does not secrete toxin, and it turned out to actually have benefits. Patient just reduce their infection rate because of the non-pathogenic strain can compete with the pathogenic strain to reduce the toxin load. So we really think if you can just neutralize the toxin, you can probably just leave the bacteria alone. Then you don't have to worry about fostering more antibiotic resistance.
And eventually the body will fight it off or not. And either way, it's not really doing any harm.
Yeah, so I mean, eventually your body, other bacteria just takes time for all the other bacteria to, take a residence in your gut.
The microbiome to reassert itself.
That's right. Yeah, it's just this bacteria, they grow really fast. So they kind of, the first come and take over, didn't allow, and it cause a lot of damage to your gut. So your gut is not able to recover. But if you allow the gut to recover without these damages, then other bacteria can kind of restore the balance in your gut.
So let's talk about how you got involved in this research and what made you decide this is where I want to go, this is what I want to study.
So my lab studies, so we're very interested in protein engineering. It's really, I'm fascinated with this ability, like the rest of evolution ever since my grad school, the ability to almost play God, in a way that we can create the proteins, we can create, these have been long time considered, the forbidden thing, something produced by nature, proteins, people cannot change them, but now with these genetic tools, we can really make many wonderful things that in the past, only God can make, right? So, and I'm really fascinated by this way to mimicking this natural evolution in the test tubes to create, fascinating proteins with new properties. Yeah, so I guess I'm interested in therapeutic proteins because I see a lot of potentials, a lot of, I guess for us particularly, I want to make proteins that can be used to fight for infectious disease. So that's kind of one of my passion. And part of the reason is that, most of the pharmaceutical companies in this country, also around the world, people are mostly focused on engineering antibodies for cancer therapy. So, and antibodies are really expensive to make. And then, antibody therapy are really expensive. So, so for cancer, we can handle it. For cancer, it's kind of rare in a general sense among the population, so we can handle it. But for infectious disease, it affects, millions and millions more people. So antibody is just not a solution to treat infectious disease, in my opinion. So that's kind of drawn me interest in this design anchoring repeat protein, because these proteins can be produced very cheaply. I mean, almost at, a fraction of the price as an antibody, just because antibody requires a mammalian cell culture to produce, which is just naturally really expensive, while the protein we are interested in, the DARPin, it can be produced literally a bucket amount in bacteria. So E. coli can very efficiently produce these DARPins. So we kind of see, use these really a protein that can be very cheaply produced. If we can engineer them to mimic the function of antibody, it maybe has a potential to treat infectious disease for much greater population. So that's kind of how I got started with, engineering DARPin, using DARPin as a scaffold to engineer therapeutic proteins. So in the lab, we also engineer DARPins against, other infectious disease. One of them is it's called EHEC. So it's a bacteria that secretes a different toxin called the sugar toxin. And then it causes diarrhea. And in that case, it causes kidney damage, especially in children. So we think, by engineering DARPins that can neutralize these toxins, we can help a lot of these patients affected by this infection.
So you mentioned bacteria. Can these techniques be used against viruses as well?
Yes, definitely. So as I said, proteins are our tools, and we can use it to treat various diseases. So another area we're very interested in is viral infections. So bacterial infection and viral infections. So specifically, we are interested in the Zika virus infection and influenza virus infection. So we chose these two viruses in part because, these are viruses that can potentially affect the huge populations, and we don't have a really effective way of treating these infections. So in the case of influenza, a lot of experts I talk to, they always say, it's not whether we're going to have a next big outbreak, it's when we're going to have the next outbreak, right? Yep. So if the next outbreak happens, are we ready for it? Well, the answer is probably not. With the medicines we have, there's no way we can handle another outbreak. So that's why I see, our DARPin has a potential because, if we can engineer these DARPin that can be rapidly produced, that is effective, then you can potentially distribute it to millions of people in a short period of time. Rather than, antibody takes a long life cycle to produce. Even though we do have antibody that's effective against this influenza infection, there's just no way we can make enough in a timely manner to make an impact.
To stop a pandemic before it can,
That's right, to stop the pandemic.
Wow, okay. And you mentioned Zika as well. I know that's been in the news in the last few years. Would that have a similar approach? Or?
Yeah, so the Zika is similar approach. So in that case, we are working on engineering proteins that can prevent the disseminated infection of Zika.
Oh, okay.
Because the Zika is a mosquito. The infection starts with a mosquito bite. So the goal is, try to engineer these DARPins that can prevent the spread of the virus from a local bite to other organs in the body.
Oh, okay.
So definitely prevent it from getting into the fetus. So
and that's where the big problem is, of course, with Zika.
The big problem, yes, that's right.
When it gets to the fetus and causes problems, microcephaly and such. So that would be very cool if you could just keep it in the arm or wherever you got the mosquito bite.
That's right.
Okay.
So that's the goal.
Fantastic. Well, we'll have to get you back on the podcast at some point to talk about how all these projects are coming.
Yes, I'll be happy to.
Well, thank you so much for coming to talk to us today.
Okay, thank you.
And thank you all so much for listening, and we'll see you next time.
Thank you for joining us on Texas A&M Health Talk, a production of the Texas A&M University Health Science Center. Visit us on the web at vitalrecord.tamhsc.edu, where you'll find answers to all of your health questions. Until next time, stay healthy.